Welcome to the Explainer. Today we're going to crack open a multi-part GCSE chemistry question from AQA. I'm going to walk you through everything, the method, the logic, and even the exact words you need to use to make sure you bag every single one of those marks.
Okay, let's dive into this. So, here's the plan. We're going to break it down just like you would in the real exam, piece by piece. First, we'll get to know the molecule itself. Then, we'll tackle the why behind its boiling point, figure out which reaction diagram is the right one, get stuck into the big bond calculation, and wrap it all up with what you really need to remember.
All right, first things first. Let's get properly introduced to the molecule at the heart of all this, propane.
And there it is. Simple enough, right? 3 carbons, 8 hydrogens. But what's really clever about this question, and maybe a little bit tricky, is that it uses this one little molecule to test you on 3 totally different things. You've got to be able to explain its properties, read a reaction diagram, and then, to top it all off, do a pretty meaty calculation. It's like a mini workout for your chemistry brain.
Okay, let's jump into part 1. This is all about why propane acts the way it does, and it's our first chance to grab some marks.
So the question is super specific. Explain why propane has a low boiling point. And that word right there, explain, is the key. It's a huge clue. It's telling you they don't just want a fact. They want a story, a chain of logic. And since it's worth 3 marks, you can bet we're going to need 3 connected ideas to get full credit.
And check this out, because this isn't just a good way to answer it. This is exactly what the AQA mark scheme is looking for. It's a perfect 3-step knockout. Point 1, you say propane is a small molecule. You could also say simple molecule. They'll accept that too. Point 2, because it's small, the forces holding the molecules next to each other, those intermolecular forces, are pretty weak. And point 3, the grand finale, to break those weak forces apart, well, you just don't need a lot of energy. See how that flows? 1 point leads directly to the next. That's a 3-mark answer right there.
Now, this is probably the most important bit of the whole section. This is a direct quote from the mark scheme, and it's basically a giant red flag for the most common mistakes students make. You have to be crystal clear. We're talking about the weak forces between different propane molecules. We are not talking about breaking the super strong covalent bonds inside a single propane molecule. Getting that difference right is everything. It's the classic trap, and now you know how to avoid it.
Awesome. 3 marks in the bag. Now the question completely switches gears. We're moving away from writing explanations and into reading diagrams.
So they give us 4 options: A, B, C, and D. 4 different graphs showing how energy changes during a reaction. But they also give us this huge piece of information. The reaction is exothermic. Honestly, that one word is all you need. It's the only clue that matters to solve this puzzle.
Okay, before I show you which one it is, let's just do a quick recap. What does exothermic actually mean for one of these diagrams? It means energy is released, right? It's given out to the surroundings. So on the graph, that means our products, the stuff we end up with, have to be at a lower energy level than our reactants, the stuff we started with. The graph has to go downhill overall. And there you have it. The correct answer is B. Why? Because it's the only graph where the products on the right are lower down than the reactants on the left. It's a perfect picture of that energy being released. That's a really nice easy mark as long as you remember what exothermic looks like.
All right, deep breath. Here comes the main event, the big one. This is a 5-mark calculation, which means we have to be super careful and methodical. We need a clear, step-by-step plan to make sure we don't leave any marks on the table.
So this is our setup. On the left, we've got the full reaction drawn out so we can see every single bond. On the right, we've got a table of bond energies. And our mission, should we choose to accept it, is to figure out the value of X, the energy of that CH bond.
Okay, anytime you see one of these questions, it all comes down to one key idea. Energy change equals the energy of bonds broken minus the energy of bonds made. But you know what? Since they tell us it's an exothermic reaction that releases energy, I find it way easier to flip it around. Let's think of it like this. The total energy released is just the energy we get back from making new bonds, minus the energy we had to spend breaking the old ones. It's the same equation, just framed in a way that makes a bit more sense for this problem.
And to make absolutely sure we get all 5 marks, we're just going to follow the mark scheme's recipe. There's a point for calculating the energy of bonds broken, a point for the energy of bonds made, a point for plugging it all into the equation, a point for rearranging it correctly, and the final point for the answer itself. It's a 5-step process. So let's get started with step 1.
Okay, first mark. This is for adding up all the energy we need to put in to break up the reactant molecules. So let's be systematic. In the propane, we have to snap 2 CC bonds and 8 CH bonds. That's our unknown, our 8X. Then we've got 5 oxygen molecules, so that's 5 O equals O double bonds to break. We add up all the numbers we know, and our total energy in comes to 3184 plus that 8X.
Right, mark number 2. Now we do the same thing for the other side of the equation, the energy we get out when the new bonds are formed in the products. We're making 3 carbon dioxide molecules, which have a total of 6 C double bond O, and we're making 4 water molecules, which have a total of 8 OH single bonds. We add all of that up, and the total energy released from making bonds is a whopping 8,542 kilojoules per mole.
Okay, now it's time to put all our pieces together. We use that equation we talked about earlier. The overall energy released, which the question told us was 2219, is equal to the energy out from bonds made, 8542, minus the energy in from bonds broken, which was that whole 3184 plus 8x chunk. Just writing that line out correctly gets you the third mark. Easy peasy.
Mark number 4 is all about your algebra skills. We just need to shuffle that equation around to get our 8x all by itself on one side. So a little bit of rearranging, and we find that 8x is equal to 8542 minus 3184 minus 2219. You punch that into your calculator, and it simplifies really nicely to 8x equals 3139.
And here it is, the moment we've been waiting for, the fifth and final mark. We just have one last simple step. We take that 3139, divide it by 8, and we get our answer. X, the bond energy of a single CH bond, is 392 kilojoules per mole. And that, my friends, is a perfect 5 out of 5 answer. And just like that, we're done. By taking it one step at a time and really thinking like the examiner, we've just nailed all 9 marks available in this question. Not bad at all.
So, let's just quickly recap what we've actually covered here. This one question has given us a masterclass in a few key skills. We now know exactly how to explain boiling points using intermolecular forces. We know how to pick an exothermic reaction profile out of a lineup, and we have a foolproof 5-step method for any bond energy calculation they can throw at us. That's a lot of learning from just one question.
So I'll leave you with this one final thought to take away. Now that you've seen the method, you've seen the common traps, what's the number one mistake that you think you can avoid next time? Is it mixing up intermolecular forces and covalent bonds? Is it a silly slip-up in the calculation? Really think about that, because figuring out your own potential pitfalls is the absolute best way to improve your exam game. Thanks for joining me on this explainer.